This is a DC voltage and current calibrator. It's made by a company called EDC, Electronic Development Corporation. It's a model 521. And this had been sitting around in my barn for a number of years, and I couldn't find any information on it. So I just happened to check the other day, and I actually found manuals for this thing. And evidently, this company, EDC, may have been taken over by Crown Height, because I found a manual from Crown Height covering the 521. Well, anyway, this is a calibration device here. It has 3 ranges, plus or minus, and this is according to the specs here that I got, plus or minus 100 volts DC resolved to 100 microvolts, plus or minus 10 volts DC resolved to 10 microvolts, and 100 millivolts DC resolved to 0.1 microvolts. Then it says it has current ranges, 1 parts per million resolution, or 6 decades, plus or minus 100 milliamps DC resolved to 0.1 microamps, plus or minus 10 milliamps DC resolved to 0.01 microamps. So that's all I know so far. I don't know if it works or not. No smoke. It lights up, and the display, it's got LED displays on it. So I've hooked up a voltmeter to the output, and I've hooked a voltmeter up, and we'll see if anything happens here when I power it up. I've got it on, well, let's see, I'll put it on the 10 volt range here. And I'm getting 167 volts. Put it on the 100 volt range. 169.7 volts. So obviously a malfunction here. So you do the negative polarity. Nothing. Or that's 0. Okay, here. Negative polarity. Here's a switch to change the polarity. And I'm reading plus 170 volts. So obviously that's not working here. Yeah, it's locked up at about 160 plus 160 volts. So don't know what the problem is, but good news is I found a schematic. So let's look inside of it. That'll be the next step. Here's a look inside the unit. Power supply section back here. A cursory examination, I don't see any signs of any burnt components. Socketed IC, here's a microprocessor here. Nothing seems really hot. I was going to look for the, it's got to have a voltage standard in here someplace. I'll have to look in the manual here. Number of relays you can hear, there's some aeromat relays you can hear clicking as you go to the different ranges. Let's see back here. I'll have to look up these devices in the cans. They may be a reference, I'm not sure. Maybe here. Yeah, I'll have to, I can't read that from here. Anyway, it's well laid out. A lot of space over here on the left. May have been for some kind of an option. I noticed on the front here there's a 1000 volt, it's got a cap over it, so there may have been an option for a higher voltage. I don't know. My Datron calibrator goes up, I think, to 1000 volts, but anyway, maybe we can figure out what's wrong with this thing. So that'll be the next step. Here's a schematic of the power supply, and this regulator here, which is plus 5 volts, is mounted on the back. It's on a heatsink. It's a TO3 style case. The other 4 regulators are here, TO220 cases, Q6, 7, 8, and 9, which is Q6, 7, 8, and 9. Q6 is a plus 15 volt regulator. Q7 is a minus 15 volt regulator. Q8 is a 15, plus 15, and Q9 is a minus 15. There's 78XX, 7800 series. So I'm going to measure here. On Q6 here, the center pin is ground and the right pin is the output. And I'm getting plus 15. Q7, which is a minus 15 volt regulator, ground is on the left and the output is on the right. I'm getting minus 15. Okay. Now we're getting to Q8, which is a positive 15 volt regulator. The ground is the center pin and the right is the output. And I'm getting basically 0.01, so I'm getting nothing. So this regulator is not regulating. Here's the input voltage, 21.68. The output voltage, 0. That's Q8, which is this regulator right here. It's a plus 15. And the last one, Q9, is a 7915. And we're getting minus 15. So the problem is with Q8 here, and it's getting pretty hot too. 145 degrees. The other one's 108, 110, 150. So either this regulator's bad, or we got a short on this output here, this plus 15 volt output that is causing this regulator to shut down. So I'll have to determine if the problem is the regulator or on the main board here. So that's the next step. If you look on the schematic here, on Q8, where the problem is, you'll find tantalum capacitors, 2 of them. And on Q8 you've got from the output to this point here, ground, you've got a 6.8 volt tantalum at 35. So I'm going to measure right across that tantalum cap here and see what the resistance is. Basically 0. So we got a short. Okay, we've got another plus 15 volt regulator here with a tantalum across, same value, 6.8 at 35. I'm going to measure across that tantalum cap, which is basically the output of that supply. And I get a little over almost 14K. So something at this point is pulling this down to ground. So what I'm going to do next, I'm going to pull this tantalum out, which they always seem to give problems here. You know, it's a 35 volt tantalum on a 15 volt supply, but that doesn't mean anything. So either we got a bad regulator, a bad tantalum, or something down the line here is pulling this point low. So the next step is to find out why. I remove that tantalum. I got it on ohms. And if I can get the leads to touch, 0.2 ohms. That thing's shorted. Okay, so before I replace it, I'm going to power it up and see if we got our, see if it's acting right. I'm going to measure that regulator again. And we get plus 15 volts. And that's what we want. I'm going to put the voltmeter right across the output. And we're still getting the high voltage here, 169 volts. Well, we still got a problem. Yeah, I have 0 dialed in to the unit here, and I'm still getting about 160 volts, 167 volts at the output terminals here, which is wrong. So somewhere, here's the output amplifier. For some reason, we've got a problem. What I'm going to do, I'm going to go back and see if the signal driving the output circuitry is okay. Now on the other side here, this is the output of the digital analog converter here. And I'm measuring at this point to ground. This is a OP07 op amp right here. This is the output op amp of the digital analog converter here. Now with 0 dialed in, I've got 4 millivolts. So now I'm going to dial in 1 volt, and I got half a volt, 1 volt. With 3, I've got 1.5. With 4, I've got 2. 5, I've got 2.5. So it looks like everything's working okay up through the DAC. Everything's working okay up to there, which is good. So now what I need to do, and here's where the input comes from the DAC to the amplifier here. So I need to find out why our output is not working here, why it's clamped up to 167 volts. So that's the next step. Here's those green caps here. I should probably replace all of them, but these test good. I had one bad one. I pulled the other one out and it looked good, but I'm going to replace them anyway. And they're tantalums. These are used in the outputs of these 3-terminal regulators to add to the stability. You don't want those things to get unstable on you there. This is a 6.8 at 35 volt tantalum. And one of my nice viewers asked that I show a little more detail. I don't like to let these videos get too long. But anyway, he wanted to show like soldering and unsoldering components. And there's different ways to do it. One of the best ways is to use a desoldering gun. And this has a suction pump that hooks up and a heating element, and this tip here, when it's running, you put it against the solder pad and push the button and it sucks the solder up. But if you don't want to do that, you can get one of these, and I've used these for many years, a solder pult. And this is basically, you arm it, it's got a spring in it, and then it pulls the solder up into it. And that's what I actually used on this one. What I did, this is plated through holes. And if you look on the other side, I'm about to solder one of the tantalums. The other one's going to come through here, but these plated through holes here, usually, as long as the plating's good, they'll make contact between both sides of the board. This has traces on both sides, so you have to make sure you have conductivity between both sides. So anyway, what I did in this case is I put the solder pult on one side, and I touched the other side with my soldering tip of my soldering iron. And from the other side, I pulled the solder out of the hole, cleared the hole. You don't want to get too aggressive because sometimes you can actually pull traces off of the boards if you're not careful. But anyway, that's what I'm going to do now. I'm going to, and when you're working with tantalums, they're polarized, so you have to be careful that you put them in the circuit right. They're marked. I'm going to turn this the other way. These are marked 6.8 at 35 volts and a little positive sign. And another little hint, especially on boards that don't have markings on it, I always put a little red dot on the positive side so I get them in correctly. If you put these in backwards, when you power it up, you'll be in for a surprise. Pull this shoe not quite to the bottom. I like to leave just a teeny bit so I can measure if I want to take a measurement. Okay, I'll solder these in place. When I'm soldering more than one component, I usually alternate. I'll solder one side and then I'll go back. That allows the other side to cool a little bit because that heat is going to be conducted up into the component and you don't want to overheat them. They'll take a little bit of tolerance. Some things are more sensitive than others. Some things are static sensitive too. You have to be careful, like I remember the old dual gate MOSFETs I used in mixers. And the early ones that didn't have protection diodes on the gates, you could just touch the leads on those and you'd blow the gates on them. Then, first you want to make sure you trim the leads. And then what I always do, got a little bottle of alcohol. And I clean the flux, which is a good idea. Some circuits it's not real critical, although you want to get it off of there because of possible corrosion, but some sensitive circuits, if you don't clean the flux off of the board, it forms a conduction path and you can upset the operation of the circuit. Anyway, that was the replacement of the two tantalums. Now we got to go and figure out why the thing still doesn't work, and that'll be next. Stand by. While I'm in here, it's a good idea to check the ESR of some of these capacitors here. This is an older unit, and they dry out and get bad, and you want to make sure that caps are still good. Anyway, before you measure the caps, what you want to do is make sure they're discharged, and make up a little device like this. It's just a power resistor, forget what it is, a couple K, with a couple leads on it. And then I can go in, of course it's not, the unit's not powered up. I just go in and go across the caps, make sure they're shorted out, there's no residual voltage on them. A lot of supplies have bleeder resistors, so they'll discharge automatically, but you don't want to trust those. Anyway, yeah, some meters have, well, like the meter on my last video here that I made has two diodes across back-to-back diodes that will hopefully discharge any capacitors, but you don't want to rely on that. This supply uses full wave bridge rectifiers, so I set the measurement frequency at 120 cycles, and you can check the ESR and the capacitance. I checked these before, they all look good. I can use my little meter I had in my last video. And we don't want the red light to come on, and we want a full scale reading here. That capacitor is good, that one's good. And if they were shorted, you know, light would come on, it would let me know. You really need an ESR meter, as I said in my last video, because capacitors are one of the big problems with electronics, especially capacitors over the last few years. Some of them, the quality isn't that great. I like working with the schematics on a monitor. I don't have a monitor over here. It's on the other bench, but it's nice that you can, you know, blow the schematic up and zero in on certain points. But this works too. Anyway, I know that the output of the DAC is good, and here's where it comes in to the amplifier section. First, it goes through. There's 4 FETs here. These are VN 0300Ms. There's 1, 2, 3, 4. This is Q 11, 12, 13, and 14. And they're located on the board right here. So I'm going to trace up through the output of the amplifier here. Here's the 2 output transistors. These Q306 and 308. Those are actually mounted on heat sinks here, and they plug into the main board here. I've still got the output pins about 160 some volts. It's so something shorted here. These run at plus and minus 150 volts here. This is minus 150. Here it says minus 150. I think this should probably be plus 150 because these are NPN transistors, and you wouldn't be putting a negative 150 on the collector of this one. That doesn't make sense. So I'm assuming that they meant plus 150 for this one. Yeah, because that's what's feeding through R309, I believe it is. That's what's feeding the collector of this. Here's test point SG, which feeds the input of this op amp, and I'm measuring at that point in the circuit. And now as I vary the input here, it's responding as it should. On the meter you can read it. Of course, the output's still latched at 160 some volts. So now we'll move on, working our way to the output of the amplifier. Okay, I've moved the probe from SG to pin 6 of Z303. This is Z303, and pin 6 is connected to the left side of this resistor. So let's see the response on the input here. And that seems to be correct. Well, here's one that was hiding on me. bad tantalum cap underneath the bottom of the board. So I got that replaced. And I found a couple bad solder joints in this area, so I redid all the connections here, and that's where the problem was. So anyway, I went down a few rabbit holes. The output transistors here were okay. At first I thought that was a problem, but I may reseat some of these chips too. These are all in sockets, and as old as this is, it may be a good time to make sure there's been no chip creep. A lot of times you push on them, you hear a little crunch. That means they weren't making contact. Here's the microprocessor here. MC68488. It's going back a few years. There's a group of relays in here. I thought maybe I was having problems with the relays too, but that wasn't the problem. All the caps checked good in the power supply. I was surprised some of these weren't going to have high ESR, but they were all pretty low. Nishikons, usually they give you pretty good results. Nishikon and Panasonics. Okay, time to give it the test here. So we'll hit the power. It's going to go through its test routine here. Check the displays. It'll check the address bus and the which we're not connected to here. And we got 0 volts. And we got 0 volts. So let's go 1 volt. We got 1 volt. 2 volts. 3, 4, 5 volts. How about 5.1 volt? How about 5.5 volts? Okay, that's looking good. Okay, let's try the 100 volt range. I'm not using the sensing leads here. Okay, here's 100 volts. And we're off a little bit here. Let's see. $90 volts. Let's try 101. That's a little closer. 102. 3, 4, 5, 6. This obviously needs to be calibrated. What I think I'll do, I have a Datron calibrator that I can use, and I also can compare this with a comparator with my 10 volt standard, and we'll see. Ideally I could take this to a lab someplace and okay, here we got negative volts, negative 100 volts, 0, positive. So you have two different polarities you can use. Let's try 0.01 volts. How about 0.02 volts? It's pretty close. Anyway, it appears to be working now. So until I can get a better standard to calibrate this thing, I'm going to leave it like it is. A few millivolts really mean nothing to me with the type of equipment I work on. It's not that important. If you were in a calibration lab, of course, it's a big deal. Anyway, we got the EDC 521 working. So I'll try to put this to use, maybe some more projects. So hope you enjoyed it, and thanks for watching. See you in the next one. Bye for now. If you're interested in this device, the 521, I found 2 manuals on the internet. This one I found on the Repeater Builder page, which they have a lot of good schematics. This one is, I believe, an older one. And this is back when the company was still EDC, Electronic Development Corporation. And this one is a little more involved than the other one I'll show in a second here. But if you want to download this, it's on the internet. I'll go down here and let's see. There's some good diagrams down here. Here's a block diagram of the instrument here if you want to take a quick peek at it. I'm not going to go over it here. It's microprocessor controlled here. And this manual here has all the layouts, board layouts, etc. You can download the manual if you want to look at it. Here's a power supply, which is probably, if you get one of these and have problems with this, first place you'd want to look. But anyway, this is one of the manuals. Now here's the second manual that I downloaded. This is Crown Height Corporation, so evidently they took over for EDC. And this manual isn't quite as detailed as the other one, although it's a little nicer quality manual. I was looking for a date on here. Yeah, this one is revised May 2003. So they must have taken over. This is pretty much the same information, although there's no detailed schematics like in the other one, just basic operational stuff. So if you are interested, just search for this manual and you can get it there. When I had picked this device up a long time ago, I couldn't find any documentation, so this, I don't know when they put it on the internet, but this is fairly recent. So it's nice to have manuals if you have to work on this kind of stuff.